Today I'd like to talk to you about some new stuff. We want to talk about complications to the simple circuits that we learned last year. There are certain things that we taught you that are true in most circumstances, but are not always true. And if you don't understand where the model that we learned goes wrong, you're going to be in big trouble when those situations arise. So I'd like to take you a little farther with your understanding of circuits. So the first thing I want to remind you of is a simple parallel circuit. I taught you something that at first glance seems to be true, but when we look a little closer, we find out there are complications to this. So I have a 6-volt battery, and we know that these light bulbs are all going to get 6 volts because they're hooked up in parallel, or so we thought. We know that when we take out one of the light bulbs, it does not affect the other light bulbs because each path is independent. They're each connected directly to the battery, so they each get the 6 volts of the battery. Seems simple. However, let's take another look at things. So I built the circuit using two 1.5 volt batteries. I've got 4 light bulbs hooked up in parallel, and I've got switches that will allow me to turn on one or more of the light bulbs at a time. You'll notice when nothing is turned on, it reads 3 volts. You'll notice when I turn on the first light bulb, it's still 3 volts, kind of. It's 2.9, it rounds to 3. But when I start turning on more and more light bulbs, every time I add a light bulb, you can see how the voltage decreases a little bit. By the time I got all 4 light bulbs hooked up, we're only at about 2.5 volts. Something is going on that we did not account for last year. Something happens in real life when you are trying to get a lot of current from a battery that we did not account for. This phenomenon always happens, but most times the currents are small enough that we don't even notice it and we don't need to take account of it. But in the case of these light bulbs, we can see it's pretty significant. So what's happening? First of all, let's plot out what we did. When we had no current, we had a voltage of 3. When we took a little bit of current, we saw the voltage drop a little tiny bit. And when we added another and another and another light bulb, we could see we got more current coming out of our battery, but somehow the voltage of the battery seemed to be decreasing. This actually forms a linear relationship. And in this linear relationship, there are 3 very important ideas you want to get from the graph. Okay, so first of all, I want to make sure you realize when you see a voltage on the battery, do not take it as the actual voltage that you're going to be getting. Depending on what the battery is doing, you may not actually read the voltage that's stamped on the battery. So here are 4 different batteries, and you'll see all 4 of the batteries say 12 volts. All 4 of them give me 12 volts when I don't have any current coming out of them. The difference is all these batteries are not created the same. The purple one you can see barely changes as I pull more and more current out of it. This battery is able to maintain almost 12 volts at very high currents. This is important when you're talking about a car battery, because a car battery might have to pull 300 amps. None of these other batteries could actually give you the current that you need from a car battery to start it. You need your car battery to have almost a perfectly horizontal line. These other batteries, although they say 12 volts, will never start your car. Because as you pull more current out of them, their voltage decreases and decreases until eventually you hit the x-axis. Once you hit the x-axis, you obviously cannot get any more current out of that battery. Okay, so let's take a closer look at one of these. Okay, when you see one of these lines, you want to look for 3 different things from the line. You want the slope, you want the y-intercept, and you want the x-intercept. And they all mean different things, but they are all tied together. So first of all, the y-intercept is easy. The y-intercept is the voltage that you're supposed to get from the battery. It's called the electrochemical potential of the battery. It's determined by the chemicals that are inside, or at least used to be inside, of your battery. So this one should have had an electrochemical potential of 1.5 volts. Okay, that's the y-intercept of your graph. The slope of your graph is called the internal resistance of your battery. You want that number to be as small as possible. You want that slope to be as close to 0 as you can get it. The bigger that slope is, the bigger that internal resistance is, the less you're going to be able to get from your battery. The more energy you're going to waste inside the battery. Finally, the x-intercept, and we don't even have an x-intercept yet, we have to go out much farther. That will give us the maximum current that we can get from our battery. So 3 important things, all related to the line that we get when we plot voltage versus current. So here's a battery that looks like it's great. The line looks almost horizontal. But notice, we're only measuring 20 milliamps worth of current. At small currents, you don't even notice that there's a slope. So all the things we did last year, they worked fine, so long as you keep your currents modest. However, if we were to try to expand this to bigger and bigger currents, we would see, this is the same data, that this line actually does have an x-intercept, and it's pretty low. I cannot even get 2 amps out of this battery. This battery is not as good as I'd like it to be. Okay, so let's say we collect a few data points. How do we figure out how good the battery is? How do we figure out what we can get from this battery? So we pick 2 points. They do not have to be data points. So here we are, 1.5, comma 14. And here we are, 5, comma 3. Okay, so you start with 2 points. And hopefully you learn from algebra, if you have 2 points on a line, you can find slope. So do that first. We have 3 minus 14 and 5 minus 1.5. So pause the video and find your slope. When I did this, I got negative pi. Not quite pi, but negative 3.14. Again, what is this number? It is a resistance. It's not a resistor, it's a resistance that exists inside your battery. Batteries have materials inside that inhibit the flow of electricity through them. Okay, that is the internal resistance of this battery. So when we write our equation, y equals mx plus b, we can put in the slope. How do we find the other things? Well, once we have the slope, we can pick either of our points and plug in. I'm going to use 5, comma 3. And I can now find the y-intercept. I get a y-intercept of about 18.7 volts. Again, if I trace this back, yeah, somewhere between 15 and 20. Looks good. 18.7, more accurate than just eyeballing it up. Finally, the x-intercept you get by using your slope, using your y-intercept, and plugging 0 in for y. 0 for Y would tell us when it's going to hit the x-axis. So go ahead and do that. And I get around 6 amps, which looks pretty good. Okay, looks really close to where it was heading. So you can figure out the 3 important things: the internal resistance, the real voltage of the battery, and what is the maximum current that I can hope to get from this battery, just by using the skills you learned in algebra class. Okay, so here's an example. So let's say we have a battery and we want to know its internal resistance. Instead of collecting a whole bunch of points, we'll just collect 2. We'll do the slope, we'll do the y-intercept, we'll do the x-intercept. So these are the numbers you can use as your ordered pair. We have a current of about 0.2 and a voltage of about 14. We have a current of around 0.6 and we have a voltage of around 10. I'm not going to do this for you. Follow the same steps we did before and figure out the internal resistance of the battery, the real voltage of the battery, and the maximum current that we can get from our battery. Again, we get it with just 2 data points. Not as accurate as doing it from the graph, but much simpler. More simple yet is to do it with just a single data point. We can only do this if the voltage of the battery is known ahead of time. So we have an ordered pair again. The first data point will be with 0 current. 0 current should give me the electrochemical potential of the battery. The other data point looks like it's around 0.65, comma 6.3. So again, I'm going to ask you to do this on your own. Find the internal resistance and find the maximum current from that battery. You obviously don't have to get the y-intercept because it's already been told to us. Finally, how do we actually use this? Car batteries. If you want to see if your car battery is any good, you've been having trouble starting your car and you want to know, is the battery the problem or is there something else? You don't just want to take the battery and touch the terminals and see what it reads, because you're not drawing any current from the battery. So you touch it and it might tell you something like this: 12.63 volts. And you say, well, I got the 12 volts that I'm supposed to get. Remember, 12 volts is the approximation. Real car batteries are supposed to be more than 12. They probably won't be 13, but 12.63 sounds great. But the battery's not doing anything. So then you hook up something, maybe you turn on your headlights, and you put a load on the battery, and you'll see that the battery voltage drops. It's now reading 9.96 volts. You need to know how much current is being drawn. So for those headlights, it's 3.5 amps. So you have your 2 ordered pairs, 0, 12.63, 3.5, 9.96. Find the internal resistance of the battery. Find the electrochemical potential, which we really already have, the y-intercept. But most importantly, find the x-intercept. What is the maximum current that I can get from this battery? In order to start your car, you might need 150 amps. Can you get that from this battery? This equation will tell us. If we can't get the 150 amps, it doesn't matter what else we do to the car, we're not going to be able to get it to start. We're going to need a new battery.